Swayam Prabha. Digital India. Educated India.
Hello everyone, let's continue now. So in the last lecture, we have been talking about the deflection, and if we apply forces and moments, so force and moments on a cantilever, and y and phi are associated deflections, what will be the relationship? So we derive the relationship between the forces and the displacement, and at the tip these are the deflections, and we can also write in matrix form here. So we may be referring to these equations wherever required. So just remember force and moments, and then deflections y and phi, the angular deflections we are talking about. So let's continue. So take this case. So suppose a rigid bar, relatively rigid bar BC is connected to a thin section AB, so flexure element, and just a 2D case, but it can be extended to 3D. So it can be a thin sheet flexure also, or it can be simply a wire as well. So what happens in this case when we apply force at the end at C? So because of the loading, and if you check at point B, what we realize that at B we'll have a forces acting at B F, and there will be equivalent moment also acting, which is M, which will be equal to F times. So if overall length is capital L and the length of the flexure is small l, so this will be the bending moment. So at B, so at section AB, which is the functional element here, the compliant part, so what will be the deflections? And what we also realize that if a force is applied at C, the element BC will also rotate at point P. So there will be a center of rotation. So what we call it instant center of rotation P. So we'll try to calculate the location of P. So just take this case, and if for AB, if we take section AB, and then at B, if we calculate the equivalent forces, so there will be force F acting downwards, and there will be moment acting at B, which is F times capital L minus small l. And if we substitute what we derived earlier, so this is the moment part. So one is because of the force, other is because of the moment, and similarly we can see we will get y and phi. So phi is the angular rotation and y is the deflection at point B. But we also realize that y and phi, they are related. So if we extend this line BC, then what we see that it is intersecting with the initial line at P. So that's a kind of pivot or the instant center of rotation for this body BC. So y equal to phi times x. So we can also calculate this x based on this. So if we try to calculate x, So y equal to phi x. So therefore, y will be simply x will be y over phi. And if we take the ratio, what we can see from here, at the top we can take f ls square by 3ei. So don't take 3, I think just take ei only common, and then what we'll have is L by 3 plus FL square common. So you will be left with capital L minus L divided by, and at the bottom EI is taken out, so it will be 2 over. Here we can take FL and EI, so F small l over EI, and then again if you take the common part, we are left with L by 2 plus FL is again out, so we will be left with L minus L. Yes, so I think if we rearrange and then yeah, this will be all cancelled out, EI, and single L will be also cancelled out. So we will be left with single L at the top, and then so if we work it out, we'll arrive at this formulation. So where x is equal to L and under bracket 3 capital L minus L divided by 3 2 capital L minus L. So this is the derivation for x, and x is the position of P from B. So if we check from A, from the fixed end, it will be L minus x, and this length is x. So be aware of that. So x is from B. So what happens if we have this case, and suppose now this force is only applied at B, so not at C but B. So force is acting at B, so there will be no bending moment. And in that case, what we realize that the capital L is equal to small l, the length of the flexure part or the compliant part itself. And when we substitute, we'll get this relationship. So x is 2/3 of the length of the compliant part, but from B. But from A, it will be 1/3. So be aware of that. And yeah, from here also we realize that it depends on where is the force applied. So capital L and small l is dependent on those factors. So it's not a fixed point. It depends on where is the force F applied. So yes, if it's applied at B, it will be 2/3. But we can also check what happens if L tends to infinity, and in that case load can be considered as a pure bending load. And what we observe that then in that case, if the pure bending moment is acting, then x will be L by 2. So it's a halfway. So if it's a pure bending moment, then it's a L by 2, is at the middle of the part AB. So for that, what we can do is we have x, we can just quickly do this by 3 minus. What we can do is we can just divide by capital L. So what happens, what we get is L 3 minus LL cancelled inside, and this smaller L over L divided by 3 2 minus small l by capital L. So when L tends to infinity, L by L tends to 0. So what happens then? This x tends to 3L divided by, because this part will be 0. So we are left with 3L divided by 6. So equal to L by 2. So that's how we can find. So if there is a pure bending moment acting on the rigid part BC, which is relatively thicker compared to the section AB. So therefore, if there is a pure bending moment acting on BC, the pivot point, the instant center of rotation P, will be halfway. So always remember that. So what happens if we have forces acting Fx, and suppose xz plane is there, and then we have this kind of arrangement, then what to do? So yes, we know that if this is the beam, and if this F is acting along the length, along the longitudinal axis, is relatively stiff, so it's A by L. So it's a axial stiffness. So if we know that there is any dominant load and the direction is more or less known, then what is important is, so this is the dominant load. So we don't have to align to x or y, but what we do is we orient that flexing part AB along the force direction. So what happens because of that force? Yes, it's the axial load coming on the flexure element, and it's a relatively rigid compared to bending and under torsion. So yes, we will orient towards that, and for any kind of moment, there will be rotation phi. And we know if there is a pure bending moment, then the P will be here halfway. So yes, if the dominant load is defined and we know, and if it's not varying too much, then it's very easy to work with. We can just orient the sheet flexure or this kind of a flexure element, the cantilever kind of thing, along that. So that's why it's saying here a single flexure may serve as a hinge when it is in line with the dominant load. So dominant load we know, and then we can align, and for any kind of bending moment, it will be pivoted at point P. So we can get a very good hinge. So this is the case we are talking about. What happens if there, like, the loads are in different directions? So this is relatively stiffer ky A by L along the length. But if Fz is significant, then what happens? This will create a bending moment and a force F, and there will be a deflection. So therefore, we'll have a stiffness Kz because of the bending load coming on that part, which will be 12 EI by LQ. So of course, in this case, very difficult to get that hinge motion or the pivot. So when we know that this dominant load is not static and the directions are changing all the time, what we can always do is we can always get the resolved into two components, Fy and Fz, and then considering Fy and Fz as a dominant load, we can put two flexures. So one along Fy and the other one Fz. So what happens, for any load, we can always get the parts Fy and Fz along that, and it will take care of that. And then for any kind of moment, there will be associated deflection, and In that case, what will happen? P will be the instantaneous center of rotation. What happens if these two are identical? So call it, because we are saying Fy and we are calling it Fz. So call it Kz and Ky. So the bending stiffness is way lower than the axial stiffness here. So suppose if we take equal length and the same area of cross section, so suppose Ky is equal to Kz equal to K, which is Ea by L. So same area and same length. So the stiffnesses are same. So what happens in that case? So if you try to make the equivalent diagram, same K, and for any force F, and there is an angle alpha, what we realize that the stiffness experienced by F, so K, call it is function of alpha, which is F over delta. What we can easily find it out, and we also discussed in the previous part when we are talking about the stiffness, designed for a stiffness, but we realize that it will be nothing but simply K, the stiffness of the individual elements. So just be aware of that. If there, so it's independent of the direction of F wherever. So no matter how we apply, whether it's in the y direction or z direction or in any inclined direction, the stiffness experienced by the force is always K. So it's a very good example of the same stiffness, same radial stiffness, just by putting two orthogonal stiffnesses, and we can feel the same stiffness in any direction. So in this case, if we just try to remember the what we discussed during controlling degrees of freedom, that these are two constraints. So one constraint C1 you call it, and one constraint C2 if we have, then actually this is the rotation point, right, axis of rotation. And from there also we know that P will be, because these two are intersecting at point P, and P will be the instantaneous center of rotation. So if it's just one, and then pure bending load, bending moment, then the P will be halfway. If we put two identical one, or yes, or in general any of the two constraints or flexures, so the point of intersection will give you the instantaneous center of rotation. So it's not lying in between the flexures, but it's away. But what happens if we let them cross? So if we let them cross, and if we just follow the same principle and the two constraints, so two constraints C1 and C2, so the C1 and C2, this point will give you the point of the instantaneous axis of rotation, that is a point P. So for very small rotation, yes, that's fine. And yes, here is it looks like symmetric cross flexures, because why we are calling it symmetric, because the lengths are same. So then in that case we just consider it symmetric, and the thickness is way smaller than the overall length, so it can flex. In two dimensions, yeah, it looks overlapping, and one may think that is intersecting, but essentially it should not overlap, because this is the arrangement we are talking about. If it's like this, then what happens? We are imposing a condition here, and we are fixing the point P. So two are crossing. So it may not work as what intended. So the behavior will be completely different. The stiffness will be way higher, and the stresses will be also higher, because here the lengths we are talking about is effective length is L by 2 only. Here we are talking about the entire length. So entire length is flexing, and that's why it's very important to understand the difference. So maybe because one is not aware, they tend to just fuse it, or maybe because of the manufacturing limitation, or if you are doing wire EDM, you tend to just merge them. But if you are merging, be aware that the relationship, the stiffness, the stresses, the range of motion is going to be very different from this case. So these two are not same. So when we consider this part, and when we are talking about this case where yes, it looks symmetric, but they are overlapping and they are not crossing each other, and they are free to deform. So what we realize, when it deforms, actually the point P moves. So but therefore it's very important to understand that we are looking for very small deflections phi. So if we want to do the calculation and want to find the stiffnesses and the stresses, first consider just one leaf spring. So just call it one leaf spring. So because of the moment and the phi relationship, EI by L, because it's a bending, so the deformation phi and M, they are related. So this is the how moment and phi in a single leaf spring. Similarly, if you are talking about the stresses, so it's My. So Y is the top or bottom layer of the fiber. So either in tension or compression, the maximum value T by 2 divided by I. And when we substitute for M here, this is what we get in terms of, so the stresses, so maximum stresses phi E times T divided by 2L. So what we realize that the stresses, if the T values are high, so if it's a thicker cross section, the stresses will be very high for the given deflection. Similarly, if for L, if L is large, so L is in denominator, so the stresses value will get reduced. So if you want to have compliance, good compliance, and want to have a large range of motion, it's better to have smaller thickness and large length. And that is the reason, if we just fix at the center, the effective length will reduce to L by 2, and then the phi will be very small. What happens in this case? Yes, so sigma and the stresses and phi are related, and is for both of the second one also, second leaf spring, it will have the same deformations, right? So it will also go to the same extent. But what happens to the rotational stiffness, overall rotational stiffness? So it will be M total divided phi, and since it's in parallel, so two acting, and both sharing the load, and therefore it's not, so for one is EI by L, but the total stiffness will be 2 times EI by L. So this is the rotational stiffness of the hinge. So now we know that if we take any kind of a cross flexure to flexures put in orthogonal fashion or in if intersecting but overlapping, and then we can get a very good hinge out of it. So what we learned that there are two kind of cross flexures we just encountered. In one, the ICs, the instantaneous center of rotation located outside the flexure, and in the other one is the halfway. So when it's outside, what we are talking about is, so two flexures. So if we just extend, this will be point P, and if we just apply any moment to this body, so it will be pivoted at point P. In the other one, if we just go like this and then have any body attached like this, but we observe that this is the point P in the midway. So we can create any kind of a hinge using two of these kind of flexures, the sheet flexures, and that's why many times it's referred as a cross flexure in the literature. So yes, we can have a very generic model, and then like L1 and L2, and it's intersecting at P, so this will be the instantaneous center of rotation. And similarly, we can have just one leaf spring over length, and this is pivoted at P. We can write the equation, so this can also bend like this. So, and here, if we apply a moment, there will be angular deflections. And overall the stiffness, we can get rotational stiffnesses, and depending on like, okay, whether we are talking about the large width to thickness ratio or same thickness as width, then this compliance factor will be different. Of course, if we need and try to calculate the stiffnesses for different kind of flexures, we can always refer to the literature, and we can find the details, and we can calculate. So this is the generic model, but most of the time we will be using sheet flexures, and we arrange them, and we can get a different kind of arrangements. So of course, we are talking about the symmetric initially. Symmetric because the lengths are same for the two parts, and it looks symmetric on 2D, but essentially when we try to fabricate, what we realize that the embodiment is not symmetric. So it's on top of each other. So I think this is the correct depiction. So isometric view. So two sheets crossing each other, and okay, this will be the preferred direction FZ. So should be at the middle, and then so this will be the bearing load, right? And we can always write in terms of Y and J. So dominant load will be taken over by these two flexures, but we can have always a moment, so we can apply this twisting moment, and we can get a hinge out of it. So this is the non-symmetric embodiment, but we can get the symmetric embodiment also, the same mechanism. But what we do, we split and then we move to the either side. So you can see that if this is HI, the inner part, so H naught, the H naught will be, the thickness will be, the width will be half of the center section, and we split and put it on the either side, and we can get the symmetric embodiment. And as such, we don't see much difference. The rotational stiffness and everything will be same. But when it comes to bearing load capacity and the stiffness, but we may realize that the symmetric embodiment is way stiffer. It's not very intuitive, but maybe we try to learn that. So what we have is now these arrangements. So like this is non-symmetric and this is the symmetric one. So you can see the center part is moving as it deforms. Same here. And these days it's very easy to create these models, and we can 3D print and we can see ourselves also. So this is like embodiment, the non-symmetric, so it's overlapping on top of each other, and then you can easily turn. So you can see that is it looks like it's a hinged. Similarly, on the other side, we can have this half weight on the other side, and we can get the symmetric one. And here also we can see that it's a hinging. So very good examples and very effective these days. We can simply develop the CAD model and print ourselves and check also how it works. But we also realize that you can hang a load and you can see that it can give a very large range of motion, and it can be can easily replace a lot of revolute joints in the machineries. So there are several embodiments. So like the similar kind of thing we did, and we can get these rotations. So we can also see that. So we have embedded a video. So these are all 3D printed parts, PLA. So that is non-symmetric. This one is the symmetric embodiment. So you can see that is flexing at the center. So similar different material, but again PLA, I think. Different sizes. We can also get in a tubular form, and then it can be easily used in any kind of circular cross sections. So very easy these days. So in order to understand what is the effect or why the stiffnesses are different, why there is a stiffness reduction in the bearing direction, so in the axial direction, and due to the eccentric tensile load. So just consider this case, and for instance, this is the neutral axis, and suppose if its force is applied at a section where at A, which is at a distance A away from the center line. So what happens because of that? There are two things happening. So equivalent, if we try to see, there will be Fx. So this is the axial force. So this is what we get, sigma x. But at the same time, if we just look at this point, there is a bending moment also acting, which will be Fx times A. And because of that, there will be also bending load, sigma b. So now you realize the stress distributions are different, and at the top there is one contribution from because of sigma x, but another contribution due to sigma b as well. And therefore the deformation, if you are talking about the displacement x at point A, if you are talking about this displacement at this point, this is because of the axial deformation, and this is because of the bending. So A times and this whatever is phi, the rotation is there because of the bending load that will get reflected. So both will get added. So of course then the effective compliance at point A will be this one. So one is because of the this axial load, and the other is because of the bending. And when we try to compare, so what if A is 0? So when it's acting at this point, so that is K naught, and Ka is the Fx over, or so if we try to find the relationship, that is the stiffness ratio we get. If it's not prismatic and some other cross section, we can define H star in this fashion. And if we try to plot the ratio, the stiffness ratio versus A by H, what we see, there is a sharp decline. So if the force is applied at a point which is above the center line, there will be a huge decline. And what we find that even for this, just at the top, if we are applying the force, so 0.5, so here if we go, so the stiffness ratio, right, so Ka divided by K naught is 0.25 and roughly 1 by 4. So the stiffness drops by a factor of 4. So just the non-symmetric embodiment and the symmetric embodiment can give rise to this kind of variation. So there is a sharp decline, and even if, so just consider the case where it's non-symmetric. This case, no matter how we apply the force, it will be not at the center, but if it's at the like middle section, so it will be only applied at some of the edges. So very difficult to visualize, but it can make a difference. But if we take symmetric one, just a split one and then put it on the other side, we can say that is asymmetric, and then we can get this stiffness. So this stiffness we are talking about is this stiffness, because this is the dominant load we are talking about. But if we pull and then rotate, it's you can see that it's very nice. Yes, we have a problem if suppose if it's a compressive load, so it's a slender part, so the buckling will come into picture, and as it deforms, that load capacity will get reduced. So it's very important to understand that what kind of loading should be there and how it should be applied. So be aware of that. Another thing we have to also remember that is a over constraint design. So one sheet flexures give you 3 constraints, and another one also give 3 constraints. In parallel combination, 3 plus 3 is 6, but we know that it can rotate, it has one DOF. So it means 6 minus 1, 5 constraints. 5 constraints should be there, but we have 6, so there is 1 over constraint. So this may give rise to some problems, and when we do the assembly, many times if it's not aligned, then there will be some deformation, warpage, and we can encounter it. So whenever you try to assemble, you will see that problem happening. So if we really want to get rid of that problem and resolve the over constraint problem, at one end what we do is we just release 1 degree of freedom. So from this end we have only 2 constraints, and from this side we have 3 constraints. So total 5 constraints, and we can have 1 rotation left, 1 DOF. So this is one of the embodiment, but there can be many variations. So yes, it's a cross again, plus cross sections, if you are talking about, is this is the cross section. It's a compliant. But knowing the or understanding the uses and how effectively it can be used, one can always try and when it comes to fabrication and realization, one can be very creative. And one very good example from Philips, and what they did is they just took thin sheet thin sheets, metal sheets, and cut in that fashion, embedded, and then you can just put a semicircular wedges and then fix it, and you can get a very good cross flexures out of it. So there are also commercial flexures these days available, so similar to what I just showed here. But here they can use brazing and all those things. So separately you can put it and braze it, and you can get a metallic piece. These days, I think yeah, one can also use metal 3D printers and can get a very good cross fractures. So there are some examples here, uh, and one can see that. So yes, here if you see the flexures, so these are the cross flexures you see here. So yeah, means this you see in the video, and this is nothing but a straight guidance mechanism, and this is based on very simple principle. So this can travel in that way, and these pivots is just replaced with that cross flexures. So again, it can be, one can make it this kind of designs and can have a very good mechanisms. One can also have, this is the parallelogram, and that's why we are getting the straight guidance. But otherwise, one can also make of any kind of 4-bar mechanism for different applications. So where you can have a rocking motion. Of course, the range of motion will be limited by the hinge design, and one should be aware of that. The another way to achieve these kind of things are injection molding, and plastics. These days, it can be very easily injection molded, and we can create parts. And these kind of designs we see in most of the commercial products, shampoo bottles or any kind of bottles where the hinge is required, that can be achieved. And what one has to be careful is through injected, so that we get this fiber alignment. So it should pass through one direction and reach to the other side, so that the length, the polymer chain should be along the hinge. And so we can create symmetric variation also. And this is one example where, like, if you don't do it nicely, the coagulation can happen at the hinges, and then it can break because it's not through injected. So if that is the case, so in the first scenario, what happens, by the time the flow it reaches here, it's a coagulated, and you will have a joint, and most likely it's going to fail from there. So if that is the case, it's better to create a break here, and then start from one side, so that the all the functional part or the hinges are through injected, and we can get a very good solution. So yes, we'll stop here, and we'll talk about more or different kind of flexure design. So today we covered cross flexures, and because many times we need a revolute joint. So in the conventional design, we use bearings or bushings, but if is for precision application, and if you want to get rid of friction related issues, or want to get rid of any greasing or lubrication, we can easily get rid of those things and we can replace with the cross flexures. Yes, the limitation will be the range of motion. So we'll continue with the different type of flexures in the next lecture. Thank you.